Okay, so let's consider the following problem, 2 variables and 1 constant. We want to find the distance from the origin, so from the origin to the curve of equation x squared y is equal to 16. And that's the green curve that I've shown here. It's the curve that is going to be equal to 16 over x squared. Okay, so that's the one. And we want to find the distance from origin to that curve. Okay, so why is that a minimization problem? Because the distance is really the minimum value between one point and a set. That's the distance between one point and a set is the minimum. Okay. The minimum value that I get if I look at all the possible points that we've got on my curve, on my green curve, and I want to find the minimum value of these distances. Okay, and that's going to be the distance between one point and the set that is constituted by the curve. Okay, so let's rephrase that as a minimization problem first, and then let's solve that using what we have done earlier. All right, so we want to minimize the distance between 0 and some point xy. Okay, where xy belongs to the curve x squared y is equal to 16. Okay, so that's we're on our way. So the distance between 0 and the point that with coordinates xy, you know that this is going to be the square root of x squared plus y squared. But of course, if we minimize the x squared plus y squared, it's the same thing as minimizing the square root of it. Okay, it's going to be located at the same place. So if we can get rid of the square root, that's even better. So we want to minimize x squared plus y squared for subject to the constraints. So one way to write this is SC, subject to constraint that x squared plus y squared, x and y, sorry, belong to that green curve. And it's just that x squared y is equal to 16. Okay? So first thing, we should look at qualification. Are there any points that are not qualified? Qualification of constraints. So maybe we could rephrase our g of xy as x2y minus 16, and we take the gradient of g of xy, and the unqualified points are going to be the one that cancel that gradient. Okay, so g of xy is going to be, the gradient is going to be 2x times y and x squared. And so this is going to be equal to 0, 0, only if x is equal to 0 and if x is equal to 0 and y has any value. But we see that when x is equal to 0, my curve is not defined. So these the points that would be unqualified actually don't belong to my constraint. Okay, so for all xy such that g of xy is equal to 0, all points are qualified as x is different from 0. Okay? All right? So I don't have to worry anymore about the qualification of the constraint. I mean, I won't have to study eventually points that are not qualified because all my points are qualified. So now let's go on. The first thing we have to do is to write the Lagrangian. So the Lagrangian function of x, y, and lambda, it's going to be f of xy, so that's x squared plus y squared, minus lambda, my constants, minus lambda, x2y minus 16. Okay, that's my Lagrangian. Next thing we do is we want the first order conditions, so the gradient of my Lagrangian in all its variables. So we're going to have gradient of f is equal to the gradient of g. So in x, 2x minus 2x 2 lambda xy has to be equal to 0. And then I will have 2y minus lambda x squared has to be equal to 0. And finally, my constraint, x2y minus 16 equals to 0. Okay, and this is again a system that we need to solve. I can factor the first part, 2x times 1 minus lambda y has to be equal to 0. And second part, I can't factor it. So the first way to cancel that is x is equal to 0, but we already know that x is equal to 0 does not belong to the constraint. Okay, if I want x is equal to 0, I will never have that this constraint is satisfied. If x is equal to 0, you get negative 16 is equal to 0, which is impossible. So x different from 0, and the only way to cancel that first equation is to put 1 minus lambda y is equal to 0. Okay, so that I've got one relation between lambda and y. What do we get? We get y is equal to 1 over lambda. Okay, so that or lambda is equal to 1 over y. It's exactly the same. Lambda is equal to 1 over y. Whichever you want. Now, as I know that this is the only way to cancel the first equation, okay, so now we found a way to cancel that equation. Let's plug what's happening in the next equation, next two equations. Is that giving me something doable? So we have we're going to make 2, let's keep y. 2y minus lambda is equal to 1 over y minus 1 over y x2 is equal to 0. And so we get 2, let's multiply by y squared is equal to x squared. Okay, so that x squared is equal to 1 over 2y squared. I can use that and plug it into the third equation. So x squared is 2y squared times y minus 16 is equal to 0. So y cubed is equal to 8. So that y is equal to 2. Now that I've got the value of y, I know that, I know that lambda is equal to 1 over 2, which is actually not very meaningful for the moment, and that x squared is equal to 2 times y squared, 2 times 4 is equal to 8. So 8x is equal to plus or minus square root of 8, which is 2 square root of 2. Okay? So that, as expected, actually, I've got two, where is my drawing? This one, okay? As expected, I've got two solutions. So we said x is 2 square root of 2 and y is equal to 2. So I'm going to have, maybe let's take another color. One solution here and one solution here. And that's going to be the minimum distance between the origin and that curve. And that minimum distance, well, it's going to be square root of x squared, that's 8, plus y is 2, so 4. So square root of 12, which is 2 square root of 3. Okay, so that distance is going to be 2 square root of 3, and that's the minimum length, the minimum distance between the origin and any point of that curve. Okay.